All right, hey everyone. So this is Chapter 7, Chemical Quantities and Reactions. Um, just going to make a couple notes before we get into today's lesson. The tests look great. Really proud of y'all. I've posted all of those grades on Cougar View, so go in there and check and make sure there's no surprises. And if something's not right, you can email me and we'll figure it out. What else? This section is kind of long, so I'm going to be kind of direct and to the point. But as always, I provided a lot of videos for certain sections that I might not spend as much time on. That way, you can go in there and if you get it quickly, great. If not, you can go in and do some more um, practice problems or watch other videos, see if something isn't more clear than what I do here. Okay? Uh, it's just important that you get the information. It's not really important where you get it from. So I'll do the best I can to try to guide you along. Um, but there's also a lot of other help out there. So those of you who didn't do well on the test, it was probably just a lack of preparation. Perhaps you didn't study the right things. And when I provide these study guides and practice quizzes, you need to go in there and make sure that you do them because I'm kind of hinting at what you're going to see in the future. So, and if I repeat something, it's usually for good reason, means that it's something you need to take with you. I might use it again. Um, so, that being said, let's jump into first, before we get into the chemical equations and reactions. Um, I want to make a note about what we've been doing. So, ions. I noticed some people were having problems with the charge associated with the ions from the last chapter on Mastering Chemistry. Um, there's another way. Oh, I just drew. I got a real whiteboard, and I have a digital whiteboard, and I just drew on my digital with my marker. Didn't make any mess, but gotta wipe this stuff off just a second. As you see, I got a lot going on. All right. So looking at a periodic table, and I'll pull up a real periodic table here in just a second. Let's see. Group 2 would be right here. That'd be hydrogen. This is lithium. That's beryllium. And that's good enough. Then you got your transition metals. We're not going to worry about that. And then you got these on the right. Alright, so this one's helium. Skipping around a little bit. And then we'll start. Actually, let's start one more over. Oxygen, fluorine, and what's under helium? Neon, I think. I'll fix that if it's not. Alright, so the concept has to do with the ions and predicting what the ions are going to be. So if you're talking about a metal or something in all of these middle regions, it's going to be kind of hard to predict, right? You may know because they tell you or something, but most of the times you're just going to have to know what the ionic charge is, right? Is it 2 plus? Is it 2 minus? How many electrons are they gaining or losing? Remember, charge is just the movement of electrons. If I gain electrons, I become more negatively charged. If I lose electrons, I become more positively charged. So the easiest way that I think about this is like football and there being end zones on the periodic table. Okay, so one end zone is over here, left of the periodic table, essentially zero valence electrons. Remember, everything in group 1 has one valence electron. Everything in group 2 has two valence electrons. Well, the end zone, the goal for these atoms on the left side, is to have zero valence electrons. So what a hydrogen will typically do is give up one electron to get to the end zone and become H plus. Lithium will do the same thing. It's right below hydrogen. It'll give up one electron as well and become lithium cation, lithium plus. beryllium in group 2 has to give up 2 electrons to get to the end zone. So it'll become beryllium 2 plus in ionic form. Alright, so that you see a pattern here, right? Magnesium's down here somewhere. Magnesium gives up 2 as well and becomes Mg2 plus. Alright, that's the left side. The right side end zone is right here through the noble gas configuration. 8 valence electrons. Actually, let me take all that off. I don't want to have that big line there. So let me just write EZ. So that's end zone on the far right side. Okay, and I'll do a little line through there. So on the right side, the fluorine, it needs to accept 1 electron. Fluorine typically has 7 valence electrons, right? Because it's in group 7. So in order to get to 8 valence electron, this noble gas configuration. Oh, I tried to write that sideways, didn't work out. God, that's ugly. Let's just take it off. In order for the fluorine to get to 8 valence electrons, it needs to gain 1 electron. If I gain an electron, I get more negatively charged. So gaining 1 electron produces a 1 minus charge. Alright, for oxygen, which is in group 6, it has to gain 2 electrons to get there. 1, 2. So my oxygen ion will be O2 minus. Okay? So that's charges of individual atoms. Now we need to start putting these atoms together to make molecules, and then we can move molecules around in what we're doing today called chemical equations, chemical reactions. Alright? So let's dive into that. I just wanted to make a note about the charges. You can kind of, I didn't mean to close this out. You will know if it's on the far left or the far right. Remember, you can't necessarily do this in the transition because they will lose and gain different amounts of electrons depending on their oxidation state, which we'll come to that later. But that's why you can't use this rule in the middle. You use it for those edges, though, every time, just about. Okay? Until further notice, you use the end zones, right? The oxygen, fluorine, even nitrogen, they're all trying to get to the right side end zone, the noble gas configuration. Everything on the left side is trying to get to that 0 valence electron configuration. And you can predict how they join up based on that. Let's look at another one, and this will kind of introduce you to chemical equations. Let's make a water molecule. Okay, so in water, we know that the basic components of water is hydrogen and oxygen. Alright, but now we need to start figuring out how many of hydrogens, how many oxygens, when is my water molecule complete. You know, why isn't it H6O10 or something like that? It's H2O, right? Why is it H2O? It goes back to those charges, right? So we know from this last little part that the hydrogen gives up 1 electron and becomes H plus. We know that the oxygen gains 2 electrons, wants to gain 2 electrons and become O2 minus. Now how do those balance, right? How many hydrogens do I have to use to balance out the 2 negative charge on the oxygen? It's 2, right? So I'll put what's called, we call a coefficient in front of the H. That means there's 2 hydrogens plus, and I don't put it there, but I can imagine that there's a 1 right here in front of the O. 2 hydrogens plus 1 oxygen will give me, and this is the yield sign. Let me erase this area. And this underline right there. I'll write this again right here. Yields. You'll see this a lot, so I'll write the word there too. Yields H2O. Okay, so we're introducing a couple different concepts right here, right? Number 1 is the coefficient. That says that everything behind it is multiplied by this number. So, for example, if I had 2H2O, that means there's technically 4 hydrogens because it's 2 times the 2 there, 4 hydrogens, and then 2 times the O as well, which means there's also 2 oxygens. Okay, so that's the coefficient. The subscript, which you see here below the 2, that indicates that this atom is a part of a molecule. Okay, so the 2 in water, if I were drawing these like in like mic uh, zoomed in atoms, right? This will be my O. These are my 2 little H atoms, my 2 little hydrogen atoms. This whole thing here is the molecule, and it actually looks like this. You can't even see where the hydrogen and the oxygen separate. Okay? So, the 2 in subscript means it's part of the molecule. The 2 in front means there's 2 of everything behind it. Alright? So, if I said 2H2O, that means there's actually 2 water molecules. Okay? But that would mean there are 4 hydrogens. 1 hydrogen here, 1 hydrogen there, 1 hydrogen there, 1 hydrogen there. Alright? So, subscripts and coefficients. Um, we're at the beginning of writing this chemical equation. And before I get into that, we need to talk about chemical reactions. So let me go and show you what you're looking at on Cougar View, all right, for chapter 7. So I've put in guided notes, which these are really cool. Let me show you these. I got them pulled up on another page. Okay. These go in the order that I'm going to teach today. Now, this doesn't match up with the order that's in the book, but this is more or less a very concise um, reiteration of everything that we're doing in chapter 7. Okay, notice that there's a lot going on here, but everything is broken down in steps, so use this to kind of work through every part of this chapter. All right? So I might break this up. We might break up the math portion and the chemical reactions and equations portion, depending on how long this takes today. All right, so let me go back to uh, the guided notes are provided. I've also got PowerPoints in here. They're also arranged in the order that I'll be teaching them. So we might stop at 7.6 today after oxidation reduction. And then I will do moles and molar mass tomorrow, just so I'm still getting it all in 1 week, but uh, it'll be a little bit more time for you on that end. All right. So anyway, carrying on with the lecture. Chemical changes. So we talked earlier in the semester about chemical change versus a physical change. Chemical properties versus physical properties, I should say. Remember, a physical property is when it changes from like a solid to a liquid or a liquid to a gas, changes physical state. All right, that's kind of how you know that it's a physical property, because it's just changing the physical state that it's in. A chemical change is indicated by other things that happen, like the formation of bubbles will indicate that there was a gas present. The gas was formed by the reaction. Change in color. So any change in color should tell you that a chemical reaction is taking place. The formation of a solid, we like to call this precipitation. Okay, so if you hear somebody say a solid precipitated out of solution, that means that, or if anything, say the actual substance, calcium phosphate precipitated out of solution. That means that calcium phosphate became a solid and fell out of the water, kind of snows, looks like a snow globe when it happens. You'll see that in lab, actually, these precipitates. When you think about precipitation in terms of rain, right? The rain is in gas form, the water is all in gas form up in the clouds, and at a certain point it starts to turn into a liquid, solidifies, if you will, becomes a solid, precipitates out the sky. We use it kind of loosely in that term, but that is also precipitate. So, and also heat or flame is produced. So, obviously, like explosions and stuff like that, those are all obvious indications of a chemical reaction. Some things will catch fire. Sometimes it's really subtle. You'll have the beaker in your hand, you'll pour in something, and then you'll feel the beaker get really warm. So that's also an indication that a chemical reaction has occurred. For the formation of gas, you might not always see bubbles, but perhaps you might smell something. Uh, Say ammonium or something like that is being given off as a reaction. You might smell the odor. You can't necessarily see these tiny little bubbles, but if you do see bubbles, then this obviously a gas is being produced. Sometimes you'll have to smell it to know that the gas is being produced. All of these are just evidences of a chemical reaction has taken place. So open up this PowerPoint in your Microsoft program in PowerPoint itself, and you'll be able to roll through and do these little study checks. Bleach. I like the bleach example because most people don't realize that you're not actually cleaning anything. If a stain is on your shirt, and this is why you use bleach on white products and not colored products, is because it's just breaking those colored bonds. So the colors that we see in nature are caused actually by the bonding of electrons and the types of bonding. So when you see color, for example, that usually indicates that there's double bonds all throughout there in resonance. The bleach just goes in there and breaks those bonds. So that's why it makes colored shirts less colorful as well. It's breaking those bonds that create that color. In white products, it doesn't matter. If I get rid of the color, it just becomes white again. White's kind of the blank slate. So interesting to know that bleach is a chemical reaction in which none of the dirt or anything is removed. The stain is just altered so that you can't see it. Okay? Um, and then the formation of a gas, formation of a flame, all indications of a chemical reaction. So now we're getting into writing chemical equations. And you just saw me kind of do this with the water molecule. Here they do it with carbon dioxide. And then they also indicate what these little symbols mean. So make sure you know what all this means. Um, Typically in lab, and in harder labs, we make you fill out all the equations with these symbols and everything. I'm not sure if you'll have to do that in your lab or not. Okay, so now we're getting to balancing chemical equations. Now I've introduced you to the coefficient and the subscript, and how the coefficient says that everything is multiplied by 2, while the subscript says that there's just 2 of those atoms, each of those atoms in a molecule. Let's do an example, and then we'll talk about chemical reactions and chemical and the examples of those equations. All right. So what's one that I can do as an example? Let's do the sodium and the nitride. So um, sodium, and just to show you what I'm working off of here. After the steps to balance an equation, we have a study check. So go through here and do these steps. Write an equation using the correct formula. So you'll be given an equation, and then you'll have to go through and balance it. Now, I'll kind of show you how I like to do it, but it's basically the same as these steps that you'll see here. Okay, I'm just going to go ahead and jump into an example because we've already kind of introduced the writing of the equation itself. All right. So for the study check, it says in a solid, remember that little subscript S means solid, plus into gas. Remember that N2 means that this is a molecule, so it's not two individual N's, it's one molecule with two N's in it. Okay? Now remember the difference between it. Two N's would be the two individual nitrogen atoms. Okay? Just want to reiterate that. Remember, if I repeat something, it's because it's important. Alright, so now the Na solid plus nitrogen gas, and then your example says that the product would be, the product is everything on the right side, so Na3N. Na3N, and that was in solid. So now my job is to see if this is balanced or not. So the way you balance an equation is just check everything on the left, count the number of atoms of each element on the left, and then see if that matches with everything on the right. I like to start with the most positively charged atoms because remember what I said about the end zones. Uh, Everything on the far left and the far right are predictable. The ones on the far left are more predictable than others, so I'll usually start with there because I know that exactly what the charge on each of those will be. We go back to there. Okay, then transition back here. So, the furthest left would be the sodium. Sodium has a 1 plus charge. I'm not necessarily concerned about that right now. Let's just count the number of sodium. So I have 1 sodium on the left side. I'll take away that. But I have 3 on the right side. So right away I know this is not balanced. And the answer to that question on the study check will be no. But let's go through and balance it. Okay? So if I have 3 sodiums on the right side of the equation, I can write a 3 in front of the sodium on the left, and that means 3 times everything behind it. That'll make 3 sodiums. Okay, so now that's balanced that. Let me check the nitrogens. I have two nitrogens on the left, and only one nitrogen, that's a 1, on the right. So that's not balanced. But what I can't do is stick a 2 in right there, okay? And I also can't add a 2 there because that changes the nature of the molecule. This molecule has to be thought of as one solid whole. I can't break it down or manipulate it like I do ions, for example. Alright, so now if I can't do that, what can I do? Let's go back a little bit. Let's erase all this. And this is where I'm at. I need to balance my nitrogens, but I can't do anything with this individual nitrogen because it's a part of this whole molecule. So what if we have 2 of the whole molecules? Right? I think I can do that. In fact, I know I can. So now that's changed my math on the sodiums as well now. So it did make the 2 nitrogens that we needed to balance this out, but I made 2 times 3, 6 sodiums by doubling the molecules. Alright, so that means I need to reevaluate this left side of my equation and balance out my sodiums. So that would be 6 sodiums plus a nitrogen molecule yields 2 of these whole sodium nitride molecules. Alright, so this is the balanced equation. That's how you balance chemical equations. Alright, we'll do one more example. Let's do one of the combustion reactions. We'll talk about what a combustion and replacement reaction here is in just a minute. But let me do this. C2H6 plus O2 yields H2O plus CO2. Okay, so all combustion reactions go through this. Like I said, we'll get to that in just a second. Let's keep balancing equations. I'm not even going to put in the little symbols behind this, but this will be a gas, that will be a gas, that would be a gas, that would be a gas. I guess I did end up putting them all there, but I'm going to take them away because I want I want room to do the numbers. I'm actually going to rewrite this because I don't have enough room. There. O2. Then let me rewrite this. H2O plus CO2. Okay, so this is a chemical equation that we might give you and say, now you need to go through and balance it. Remember, I like to start with the more positively charged molecules, but there are certain orders you could do. So hydrogen, let's start with hydrogen. I have 6 hydrogens in this molecule, and then I have 2 in this molecule. So I would need 3 waters to make the 6 hydrogens to balance out the ethane on the other side. So that takes care of my H's. Now let's move on to carbon, which is the next most positively charged ion. The carbon, I have 2 on this side. I have 1 here, so I can just do a 2 there to balance those out. That's easy enough. Now the oxygen, I have 2 on this side. I have 3 oxygens there, and then 2 times 2 makes 4. So let me do 3 plus 4 equals 7 oxygens. So that one's going to need some work because I can't put nothing times 2 equals 7, right? Unless I do 3 halves or something, but you can't do that. You can't halve a molecule. You can, but we're not for these purposes. Alright, so now I got to back up and I got to figure out a way to balance these oxygens. Alright. Whenever you run into this problem where you have a half of something, you can just multiply it by 2. Because anything over 2 times 2 is itself. So we're going to multiply everything times 2 and then try to balance it again. So 2, 2, that'll make this one 6. That'll make this one 4. Okay, so make sure y'all can still see this 2 there. Alright, now let's go through and do our balancing again. I think everything should be fine up to the oxygen. Now we're at oxygen. I have 4 oxygen there. I have 6 oxygen there. 4 times 2 is 8. So this would be 6 plus 8 equals 14. So now I can actually balance this oxygen by saying seven, right? 7 times 2 is 14. Take that all back. The 14 oxygens on this side match up with the 14 oxygens over here. Oh, don't do that. Over here. Okay? So that's how you balance a chemical equation. Remember, I don't really want you to have the halves in there. So try to go through, find the lowest common denominator, multiply by 2, and then rebalance your equation. Alright? So 2C2H6 plus 7O2 yields 6 waters plus 4 carbon dioxides. Alright? So everybody should see how that math works for balancing chemical equations. Now I'm going to get into the different types of chemical reactions that we're looking at. Alright? So this is more practice. You can go through, oh yeah, I forgot to mention the polyatomic ions. So real quickly before I get into the different types of equations. A polyatomic ion, let's take PO4 for example, 3 minus. A polyatomic ion is multiple atoms that are grouped together but move together as a molecule. Remember we said that the Na3N in this case was all one molecule and I can't break it up individually into different NAs and nitrogens. Um, that's the same concept with the PO4 or any polyatomic ion. You cannot break this down into an individual phosphorus and 4 different oxygens. This phosphate moves around together and it holds this 3 minus charge all the time. So if I were to write this in an equation, say I have 3PO4, 3 minus, this is actually means I have 9 negative charge, right? 3 times the 3 minus, because every individual phosphate carries that 3 minus charge. So 3 of those would end up being 9 minus in charges. So that's kind of how you have to think about balancing polyatomic ions. Every polyatomic has a charge, and then when you move it, you move all of those atoms with that charge. So, what's another example I can think of? Ammonium, right? Ammonia typically is NH3, that would be neutral. I add an H on there, it becomes ammonium, and it has a positive charge. And so when I move it around, I have to move it in H4 in brackets, right? Like so, say there's 2 of them. This is actually 2 ammoniums and will result in a 2 positive charge overall. Okay? So just keep all those things in mind. Polyatomic ions, we'll work with those a lot more, so you'll get to get some practice in with those. But and I also provide a chart when necessary that has the actual polyatomic ions you should be looking for. There's only about 7 or 8 that you'll ever see probably, and it also had the charges associated with those. Okay, so a lot of balancing equations. Sulfate. Here's one with a polyatomic ion. The sulfate stays together, right, and it has a 2 minus charge. So that's another practice example. All right, the types of equations. And just in case you didn't notice, when we go through this in a slightly different order, so like I said, I'm going to do the math later. We're doing sections 7.4 and 7.5 first, and then we'll go back and start looking at moles and molar mass in the next lecture. So like I said, I'm going to split this up into 2 lectures so that it's not just, a solid hour and a half straight. All right, so different types of chemical reactions. I like to think about this. An example that you'll see a lot is like putting together a bike. Right. So when I do chemical equations, like when we did the 2 hydrogens plus 1 water equals or yields, I put both of them there just then. Yields H2O. A good way to think about this is like putting together a bike. Okay, so the 2 H's, and I think the book probably has a picture or something like that, is why I keep using this. But imagine I'm putting together, gosh, I don't know, a little bike here. Okay, so my parts, this would be like the water molecule right here, but my parts would be the individual tires and then the frame, right? That's my little bike frame. So it takes 2 tires and 1 frame for me to make 1 bike. Okay? So this brings up this idea of parts, right? I have to have 2 parts to make 1 molecule. And you'll see that when we start getting into moles and molar mass and stuff. You'll have things that call limiting reactions. Say I had 11 tires in the shop, right? but I have 10 frames, and then somebody will say, well, how many bikes can you make? Well, technically I can only make 5 bikes because I have to have 2 tires every time I make a bike. Okay, and then I'll have 1 tire left over. So 5 bikes is the most that I can make, even though I have 10 frames. That's the kind of thinking that you need to be in when you're doing these chemical equations. All right, we're putting together this big, we're assembling this big part, and each of these reactions does different things. So the different types of chemical reactions you'll see are listed here, and they got these little shape symbols that kind of do. You can also do like A plus B. Here goes the A plus B equals AB model as a way to express it. So let's just talk about each one of these individually. Okay. So the combinations means that I've got two different elements or compounds, and I combine them to make one product. Okay. The sulfite here, sulfate, that is sulfite, and that's not a polyatomic ion in that form. Once it reacts, it is a polyatomic ion in this form. But that's an example of how it can be a molecule with another molecule making one different molecule in a combination reaction. It doesn't have to just be one atom plus a different kind of atom equals a molecule. Okay? It can be molecules plus molecules equals a different molecule. So that's an example of a combination reaction. A plus B equals AB together. All right. A decomposition is just the opposite. I break it apart. A and B together breaks down to make A plus B. All right. Easy enough there. Single displacement or replacement means I take an atom that is connected to one molecule and I connect it to another molecule. Okay. The atom's still connected, but it's connected with something else. So that just we just trade partners essentially. Then there's also the double replacement where both partners switch places. Okay, so AB together comes in contact with CD together, and then they swap partners, become AD plus CB. All right. And then the combustion reaction, which is what we just did on the balancing equations. Combustion is really simple. It's always burning something, and it always includes oxygen. So a hydrocarbon, any kind of CH that you see here on the left side, CH4, C2H6, even if it adds an O, it becomes carbohydrate. But we call these hydrocarbons because they contain mostly just carbon and hydrogen, and then they burn in the presence of oxygen always to create carbon dioxide and water. All right. So this is always a combustion reaction. You'll see this a lot. I like to use this a lot for balancing purposes because you get to work with multiple atoms, and you'll have that case where you have an odd number of oxygens a lot of times. So it kind of makes you know balancing equations more detailed. All right. Okay. Um, yes, more study checks on the different types of reactions. Oh, yeah, the last one I want to mention is an oxidation reduction reaction. Okay, now this one is a particular interest because it explicitly talks about the transfer of electrons. So we are changing the state, the electronic configuration, if you will, of one of the atoms in this type of reaction. And so it's almost always a metal. I'm pretty sure it's almost always a metal involved because, as I said earlier, those are really the only things that can accept and lose electrons. Okay, so look for a metal, and it's kind of the first indication that it might be an oxidation reduction reaction. All right. Other than that, I mean, the important things to take away from this is number one, an oxidation is whatever is losing electrons. So when I give up electrons, and is typically has something, oxygen is involved in the process in most of these things. So that's how it got the term originally, oxidation. Uh, but a reduction is something that gains electrons. So uh, I like to think about it. There's a, I think there's a saying called oil rig. Is that right? Oil, as in oxidation, is loss of electrons, and then rig, as in reduction, is gain of electrons. So let me write that down. I don't know if that's actually written down here. Okay, I think it might be in your text. Oil is loss of electron, so oxidation. That's not a good way to illustrate it. Oil rig. Okay. So it's oil rig and its oxidation is loss. That's how they do it. They do something like this. Oxidation is loss and reduction means gain. Okay, so oil rig. That's how I remember. Oxidation is loss, reduction is gain of electrons. Okay, so that's the only really other reaction that you'll have to worry about. And you probably won't see it that often, but just know that there's probably a metal involved, and it is changing the oxidation state of that metal in some way or another. Okay, so I think this will actually be enough for everybody to get through reduction. Yeah, all right. And there's a lot of slides here on oxidation and reduction. I don't spend that much time on it usually. So it's important to know, important to recognize. But I mean, once you understand what's going on, just go ahead and move on. Don't spend too much time diving into all of this, because I won't be. I mean, unless you want to, I won't be spending that much time on these certain things. So yeah, I think this will get you at least through the lab. I'm pretty sure it will get you all the way through the lab. I will post the next video on uh, the math portion with moles and molar mass. I haven't really decided. I'll probably do it tomorrow because I'm getting vaccinated on Thursday. So I'll probably go ahead and post it and then just give everybody extra time to get the Master in Chemistry done. So Master in Chemistry won't be up tonight. I'll wait till I do the math portion before I post that. Although I will post the lab and all videos related to that, because I believe you can do everything here without calculating moles, molar mass. Okay, I think you can do everything in the lab just with what we've done here today. Okay, so that's it. I will see y'all later.